Hi, everyone. I just want to do one last very short video on multiple regression and tell you a little bit about why I like it. As you know, in ANOVA, we can do factorial ANOVA and add two factors. Once we start adding that third and fourth factor, we move to three-way ANOVA and four-way ANOVA. And those, I have seen a couple of published articles with three-way ANOVA, but not four-way ANOVA. Definitely not five-way ANOVA. It starts to become overwhelming. And yet, in multiple regression, which is basically ANOVA but with continuous variables, so the computer goes in and calculates f in the same way, but now we've got continuous variables. It is common for people to add five, maybe, variables as those independent variables, as factors, so to say, in regression. And so, especially here on UW campus, we have students in the field of ecology who are looking at maybe the sage grouse population, and they actually live in the field, and so they measure different types of plants that sage grouse might use for shelter, for food, perhaps for a place to nest their young. They also look at bugs. They look at weather. They look at structures within a certain number of feet. So, how many feet to the nearest natural gas well? How many feet to the nearest oil pump? How many feet to the nearest road? And you can imagine these ecology students end up with a spreadsheet of maybe 20 to even 30 independent variables. These are those input variables that in ANOVA SPSS calls a factor. Well, in ANOVA, this would be a 20-way ANOVA. This is too much. And so when we have something like this, we do a multiple regression. In multiple regression, theoretically, we're actually allowed to put all 20 of those in. Notice if you read if you read this section in Chapter 8 on multiple regression, Field gives a very good warning. Don't put everything in, and he's right. Sometimes if you've got 20 variables that you'd like to input, be thinking about, are they really all important? Are there two variables that are basically saying the same thing? With ecologists, they found that any variable that measures the amount of plant growth in the area was highly correlated to other plant growth. So plant growth had to do with actually with rainfall, which was also highly correlated. And so they combined all the plant growth variables into one overall input of rainfall and abundance of plants. Um, and you could do the same thing if you're using socioeconomic status. You're also using maybe free and reduced lunch. Maybe those two are basically saying the same thing, and so you don't need both in there. And sometimes you can go ahead and let SPSS tell you that. For example, let's pull up this album sales data set that Field uses, come into Analyze, and come all the way down here to Regression. I just skipped it. In Regression, we're not going to do the automatic linear modeling. We're going to come down to linear because we have a little more control here. Okay, so click on linear. And then the thing that I'm interested in his data set is album sales. So this would be a data set that our students over in the College of Business and Marketing would use. Their goal is to sell as many albums as they can. Well, what are some of the things that make a difference? Certainly, I would think their advertising budget is huge. So I'm going to put it in. And they call this block. But this block, these are the independent variables, also called factors in ANOVA, that might make a difference. I'm going to put number of plays on the radio because certainly the more a song is played, the more likely people are to buy that. And then Field, of course, added attractiveness of the band. This is actually something that our marketing people can control. They can perhaps hire consultants who can make the band look very attractive. This could sell more albums. I don't know. It's worth looking at. SPSS has this really neat method called stepwise. And what SPSS will do is it will look at the correlations because correlation is it is related to both regression and ANOVA. You remember we used correlations to decide that maybe we should include a covariate. Kind of the same thing happens here. So I'm actually going to ask for descriptives here because I want to see these correlations. Here we go. I can get a partial correlation table. Okay. I also, I think that's good. I'm good. Okay, so I've got stepwise regression. I'm going to ask for correlations. I'm going to go ahead and hit OK. Just make sure that you know which is your dependent variable. And this is the variable you're asking the research question about. How can I improve album sales? That's what I want to know. Okay, so here's my output. Here's regression. Here are my descriptive statistics. Always put these in your paper, remember. In fact, let's see, does Field may not do quite as good a job with that as I'd like. But if you look on page 339 and 340, he does report his output in here. He has T values and F statistics. I don't think he has his means and standard deviations in here. So we're going to do a better job than Field. We're going to include those in our table. Then we come on down here. Here are our correlations, and I just want you to notice this. Album sales, this is how correlated they are to the advertising budget, 0.578. That's good, that's high. Even more high for number of plays on the radio, 0.599. And then they are also correlated to the attractiveness of the band, 0.326. So all of these are correlated to album sales. Notice they're also a little bit correlated to each other. For example, here, number of plays on the radio is correlated a little bit to attractiveness of band. The correlation is 0.18, so that's very small, very weak, but still there's a little bit of a correlation there. So when we talk about attractiveness of the band and number of plays on the radio as two ways of predicting album sales, we have to remember there's a little bit of overlap between the two also because they are correlated. So in stepwise, the SPSS grabs the highest correlation. So right here it starts with number of plays on the radio. And it puts that in first. And it looks to see with number of plays on the radio, is there a significant ability to predict album sales? Well, yes, there is. And this probability to enter it is 0.05. And F is less than 0.5, so we can say, yes, there's a significant influence of number of plays on the radio. We don't need to remove anything yet. Let's add in advertising budget. Now, advertising budget was the second highest correlated. When we put advertising budget in, F is still less than 0.05, so these two together are still significant. Sometimes what happens is when we put something else in, the first one becomes less significant and even possibly has to be removed. In this case, that's not true. Let's go ahead and add now the third highest correlation, attractiveness of band. Our F is still less than 0.05, so this whole thing, this whole regression is significant. And we don't have to take anything out. If you can understand, it's possible that by the time we add these two, number 2 and number 3, number 1 is no longer significant and we would have to take it out. So I love about stepwise, it plays a little bit back and forth. Okay, let's put this guy in. Let's see what happens to the others. Because when these are correlated with each other, sometimes in the example I gave, SES, it becomes significant and it no longer matters. The inclusion of free lunch, for example, no longer matters in the regression because SES is accounting for that variability. Okay, so let's look at our ANOVA table. Isn't that just, it cracks me up that the regression results are reported in an ANOVA table. We can also look, I like this model summary. Sorry, we'll skip back up. Model number 1 was the model with only plays on the radio. Oh, sorry. And the R squared for that was 0.35. That means 36% of the variation in album sales comes from the number of plays on the radio. But then when we add our advertising budget on top of that, now 63% of the variation can be accounted for by plays on the radio and our advertising budget. What about the attractiveness of the band? Well, that is now 67% of the variation can be accounted for by plays on the radio, advertising budget, and attractiveness of the band. Notice that attractiveness of the band only moves us from 63 to 67%, so not a whole lot. What happens is every time you add one more predictor into your regression model, the R squared does go up. But sometimes those predictors are kind of nonsense. They're not even statistically significant. And so one of the great statisticians out there came up with an adjusted R square. And it actually punishes you a little bit for continuing to add predictors. So if the adjusted R square actually goes down when you add a predictor, then that's not a good predictor. You want to get rid of it. In this case, the adjusted R square continues to go up from 36 to 63 to 66%. So we're good. We want all three of those predictors in our regression equation. And if you look at page 338, Field has the regression equation in there. And he uses the numbers from this ANOVA table. Well, actually, no. This ANOVA table tells us that these models are all significant. And he comes down now to the numbers from the coefficients table. These betas actually end up being helpful numbers. And so here he's got numbers for, we've got in this last model that's got number of plays on the radio, it's got advertising budget and attractiveness of band. We've got these betas, these, I guess we should look at the standardized coefficients here. Field has got 26.61. So he's using the unstandardized betas. This B right here is a B. He's using unstandardized betas because he wants you to be able to plug in the raw numbers without having to standardize them or fix them in any way. We also have standardized betas here that allows us to see if our T statistic is significant. And notice here, just in the same way that the ANOVA table shows us, the number of plays is significant, the advertising budget is, and the attractiveness of the band. All of these have p-values less than 0.05. But here now we can actually plug right over here, sorry about this, our constant, which is 26.61. See, that's where on page 338 he gets the constant. Then he uses plus 0.08 times advertising right here. And then he uses 3.37 right here times airplay. And he uses 11.09 times attractiveness. And he actually can come up with a prediction formula that tells you what dollar amount of sales can you predict based on how many times a song was played, what the advertising budget was, and how attractive the band was. So it's a powerful way of predicting something. that we don't quite have in ANOVA. And then if you'll turn the page over to page 340, he actually reports these unstandardized betas and he tells you what each one means. So this value indicates that as the advertising budget, so look at advertising budget, as it goes up by 1 unit, which in this case is 1,000 pounds. So for every 1,000 pounds that you add to that advertising budget, the amount of money, and once again, we'd have to look at the unit, that we will receive in album sales. In fact, we can look at thousands. Oh, it's not money, it's actual flat out album sales. So you have zero point 0.8 times 1,000 album sales. You will sell 80 more albums for every 1,000 pounds that you put into the advertising budget, accounting for radio plays and attractiveness of the band. So I realize that that's a lot of information, but it's kind of like looking at it in terms of ANCOVA. We're accounting for plays on the radio, attractiveness of band. We're trying to hold those constant. If you don't make any change in either of those, but you add 1,000 pounds to your advertising budget, you are going to sell 0.085 times 1,000 more albums. So it's actually 85 more albums, okay? We could say the same thing with attractiveness of band. If you can increase their attractiveness by 1 point right here, you will sell 11,000 more albums. That's a lot. I wonder if you're selling more to the teenage girls. Who knows? But anyway, so these are not only significant, not significant in terms of answering a hypothesis test, but they bring with them so much information. We can look at each of the variables and see if we held the others constant, how much of a change in one variable would change our dependent variable, in this case, album sales. And we can also look at the overall model, come up with an equation, and allow people to predict, well, let's play with this number, or we know the band's attractiveness is never going to increase. We're stuck with that one. But what about advertising? What about radio plays? It's a powerful tool. It's fun. I'm putting this video out there so that you can watch it sometime when you're really bored this summer, just because regression is cool. And hopefully you'll have a chance to take Ed Research 5620 and play with regression a little. Thanks for watching. Thanks for hanging in there with me this semester.